Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we will continue our discussion on Introduction to Group Theory. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID. My mail ID is sanjay.vishwas@gnit.ac.in. So before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture, we have discussed about the introduction of group. And this is my first lecture on the module algebraic structure. So in this lecture, we have discussed about the introduction of algebraic structure, and after that we have talked about the binary operation on the group theory. And after that we have discussed about the algebraic structure of group theory, and then we define the elementary properties of group, and some illustrative examples we have discussed in the previous lecture. So today we will continue our discussion on the introduction of group. This is my second lecture on the algebraic structure. So here is the content of today's lecture. So today we will continue to discuss about the integral power of an elements of a group, and after that we will study on the order of an elements of a group, and then we will study on the theorem on order of a group, and after that we will talk about the residue classes on the order of a group with module M, and then we will talk some related examples on the group theory. Let us begin with the integral power of an elements of a group. So here is the definition of integral power of an elements of a group, or some properties and examples. So let G composition be a group and A be an element in G. Okay, so you know G composition be a group, but G is a non-empty set, and G composition satisfies the four properties. You know that I have already mentioned in the previous class. The fourth property, they are closure property, associative property, identity property, and inverse property. If G composition satisfies these four properties, then we say G composition be a group. Okay, so where G is a non-empty set. So let here G composition be a group and A be an element in G. Okay, so then if n is a positive integer, then we define a to the power n. Okay, so a to the power n is equal to a composition a and up to n factors. So here composition is a binary operation. Okay, so obviously a to the power n is belongs to G. Why? Because G composition is satisfy the closure property. So G is a group. So G composition satisfy closure property as well as associative property. You know that. So a to the power 2. So I will take a to the power 2. So a to the power 2 is equal to a composition a. So a composition a, if G composition satisfy the closure property, so a composition a is belongs to G. That means a square is belongs to G. Now I will take a to the power 3, and a to the power 3 is equal to a square composition a. That means a composition a, and a composition a satisfy the closure property. That means a to the power 3 is belongs to G. Okay, where G is a closed. So obviously a to the power n, that means a composition a up to n factors is belongs to G. Why it is belongs to G? Because G is closed. Okay, and G satisfies the closure property. So that's why a to the power n is belongs to G. And also we define a to the power 0, and a to the power 0 is equal to n. Okay, this is the identity element, and identity element is lies in G. So as a to the power n is belongs to G, So a to the power n whole to the power minus 1, that means inverse of a to the power n, and G is a group, so a inverse is also lies in G. So we define a to the power minus n, and a to the power minus n is equal to a to the power n whole to the power minus 1, and we can write it a to the power minus n is equal to a to the power n whole to the power minus 1. Okay, so here n is a positive integer. So therefore a to the power minus n is equal to a composition a and up to n factors whole to the power minus n. So that means a to the power minus 1 composition a to the power minus 1 composition a to the power minus 1 and up to a to the power minus 1 to n factors. Okay, and this is equals to a to the power minus 1 whole to the power n. So therefore, from the integral power of an elements of a group, we have seen that a to the power minus n is equal to a to the power minus 1 whole to the power n, as well a to the power n is equal to a to the power n whole to the power minus 1. Okay, and both the terms are belongs to G, where G be a non-empty set and G composition be a group. Okay. And after that we will take an example on integral power of an elements of a group. So in additive groups Z plus. So here Z is a non-empty set and Z is a set of integer, and plus is the binary operation. Okay, so if n is a positive integer, so we have a to the power n, and a to the power n can be written as a plus and up to n terms. So in that case, where plus is the binary operation. Okay, that is composition is plus, and this is equals to n into a, and a to the power 0 is the identity element and it is equals to 0. So in addition, you know that 0 is the identity element, and in a multiplication 1 is the identity element. Okay, in a group G composition, and a to the power minus n, and it is equals to minus a plus minus a and up to minus a, and this is equals to minus n into a. So 0 is the identity element in that group Z plus, and a to the power minus n, that is the integral power of any elements of the group, that means a to the power minus n, and it can be written as minus of n into a, and a to the power n can be written as n into a. Okay, and after that we will take a theorem on the integral power of an elements of a group G composition. So let A be an elements and Mn be two integer, and then a to the power m composition a to the power n, and it is equals to a to the power m plus n. This is the first theorem, and are the first properties of the integral power of an elements. And the second property, it will be a to the power m whole to the power n, and it can be written as a to the power m into n. Okay, and for all a belongs to G, and for all m comma n belongs to Z. So these two are the properties of the integral power of an element of a group G composition. And after that we will discuss about the order of an element, or define the order of an element of a group. So let G composition be a group and A be an element in G. Then the order of A is the least positive integer n, such that a to the power n is equal to E, where E is the identity element in G, is denoted by order of A. So if there exists no positive integer n such that a to the power n is equal to E, then the order of A is said to be infinity or 0. So this is called the order of an element of a group. So that means A be an element in a group G, then the order of an element A is the least positive integer n such that a to the power n is equal to E, where E is the identity element and is denoted by order of A. And if there exists no positive integer n such that a to the power n is equal to E, then the order of A is either infinity or 0. Okay, this is the definition of order of an element. So for example, we consider the group G composition where G is equal to 1 minus 1 I and minus I. So here G with a set with 4 elements, 1 minus 1 I and minus I. Okay, and order of this group is 4. So the number of elements is the order of a group. Okay, so G is a finite set and G contain 4 elements. So order of G is equal to 4. Okay, so here 1 is the identity element. So therefore order of 1 and it is equals to 1. That means 1 to the power 1 is equal to 1, where 1 is the identity element. So order of 1 is 1. Okay, order of minus 1, and you know that minus 1 whole to the power 2 is equal to 1. So order of minus 1 is equal to 2. So applying this equation, we will get the value of n, and it is equals to 2. Now we will find the order of I and minus I. So order of I, and it is equals to 4, because I to the power 4 and it is equals to 1. So 4 is the least positive integer such that I to the power 4 is equal to 1, as well as I to the power 8 is also 1, I to the power 12 is also 1. Okay, but 4 is the least positive integer such that I to the power 4 is equal to 1. So 4 is the order of an element I, as well as order of minus I, it will be also 4. Okay, so minus I whole to the power 4 is equal to 1, as well as minus I whole to the power 8 is equal to 1, minus I whole to the power, that means the multiple of 4 is the of a power of minus I, it is equals to 1. But 4 is the least positive integer such that a to the power n is equal to e, that means I to the power minus I whole to the power 4 is equal to identity. That means order of minus I and it is equals to 4. Why? Because minus I whole to the power 4 is equal to 1. So there is a theorem on order of an elements of a group. The order of every element of a finite group is finite and is less than or equal to the order of a group. And the very important thing of the order of an group is that the number of elements, when G is finite set, then the number of elements of a group G composition is said to be the order of a group. Let us move on the next slide. So in this slide we will discuss some theorem on order of a group. So this is the second theorem on order of a group. The order of an element A of a group is the same as that of its inverse A inverse. Okay. So order of an element A of a group is same as the order of a inverse. That means order of A is equal to order of A inverse. Okay, this is the second theorem on order of a group. So here is the proof of the second theorem. So let n and m be two finite order of A and A inverse respectively, where m is not equals to n. Okay, so then order of A is equal to n. So by definition of order of a group, it can be written as e to the power n is equal to e. Okay, so when e be the identity element. Now applying the integral power of an element of a group, we are seeing that a to the power n whole to the power minus 1 and it is equals to e to the power minus 1. This imply a to the power minus 1 whole to the power n and it is equals to e, but you know that inverse of an identity element is identity. Okay, so in that case we have applied the integral power of an elements of a group. Okay, so a to the power n whole to the power minus 1 is equal to e to the power minus 1 whole to the power n and it is equals to e. Okay, so therefore order of A inverse, and this is lesser equals to n. So this imply m is lesser equal to n. So, and you know that I have taken the order of A inverse is equal to m. So from this we will get m is lesser equal to n, and we can write it equation number 1. So after that we will take order of A inverse and it is equals to m. Okay, so from this we will get A inverse whole to the power m is equal to e. From the definition of a order of a group, we have a to the power minus 1 whole to the power m is equal to e. So and this imply a to the power m whole to the power minus 1 is equal to e. Okay, so this equation or this relation implies a to the power m is equal to e inverse. Okay, so now taking inverse on both, we will get this one, a to the power m is equal to e inverse, and you know that e inverse is equal to e. So inverse of an identity element is identity. So this equation implies a to the power m is equal to e. So therefore order of a is lesser equal to m. So that means n is lesser equal to m, and you know that while n is the order of an element a and m is the order of a inverse, so that means n is lesser equal to m, and we can write it equation number 2. Okay, so in virtue of equation 1 and 2, or combining these two equations, we will get n is equal to m. So that is order of a is equal to order of a inverse. So next, let the order of a be infinite. So in a finite case, so this two orders, that means the order of an element a of a group is same as the order of its inverse. Okay, for finite case. And next we will prove that this theorem is also true for infinite case. That means let the order of a be infinite. So then the order of a inverse is infinite. Okay, we will show that. Because if not, then order of a inverse is equal to m, and m is a finite. Okay, we consider this. Order of a inverse is equal to m, and m is a finite number. So this implies a to the power minus 1 whole to the power m, and it is equals to e. Again, applying the properties of integral power of an element of a group, we have a to the power m whole to the power minus 1 is equal to e. And again we take inverse on both, we will get a to the power m is equal to e. So therefore order of a is equal to m, and this implies order of a is finite. So there is a contradiction. You know that I have taken the order of a is infinite, but when we take order of a inverse is finite, then from this we will get order of a is finite. So this is the contradiction. So hence the order of a inverse is infinite. So in both cases, that means in a finite case as well as in an infinite case, the order of an element a of a group is same as that of its inverse a inverse. That means order of a is equal to order of a inverse. So here is the proof of the second theorem on order of a group. So after that we will take another theorem, that means theorem number 3 on the order of a group. So here is the theorem. Let A be an element of a group G composition of order n. Then a to the power m is equal to e if and only if n is a divisor of m. This is the theorem. So G composition be a group and A be an element of a group G composition. That means A is belongs to G of order n. That means a to the power n is equal to e. And if a to the power m is equal to e, then n is a divisor of m, and when n is a divisor of m, then a to the power m is equal to e. That means a to the power m is equal to e if and only if n is a divisor of m. This is the third theorem on order of a group. So here is the proof of the third theorem on order of a group. Let's start. Let n be a positive divisor of m, then there exists an integer q such that, where q is the quotient, you know that when n is a positive divisor of m, then there exists an integer q such that nq is equal to m. So in that case, where q is the quotient and remainder is 0 in that case. Okay. So therefore a to the power m, and it is equals to a to the power n cube, where m is equal to n cube. Okay, now applying the integral power of a group of an element, a to the power n whole to the power q. Okay, it can be written as this: a to the power n q is equal to a to the power n whole to the power q. You know that order of an element A in a group G composition is equal to n. It is given. So a to the power n is equal to e. By the definition of order of a group, it is equals to a to the power n, and a to the power n is equal to e, where e is the identity element. Okay, so from this we will get a to the power n, and it is equals to e to the power q. Okay, where a to the power n is equal to n, and you know that power of any identity element is equal to identity. So therefore a to the power m is equal to e. And conversely, let a to the power m is equal to e. So from this we will prove that m is a divisor of m. So since order of a is equal to n, and this is given, the order of any element of a group G is n. Okay, so n is the least positive integer such that a to the power n is equal to e. Okay, the definition of a order of a group. Again, m is an integer. Then by the division algorithm, there exists an integer q and r such that where q is the quotient and r is the remainder. Then from division algorithm, we have m is equal to nq plus r, where r is lies in 0 to n. That means 0 less or equal to r less than n, where r is strictly less than n. Okay, in that case, where r is the remainder and q is the quotient. Okay, so therefore a to the power n is equal to v, and this implies a to the power n cube plus r is equal to v, where you know m is equal to n cube plus r. So this implies, and a to the power n cube plus r, and it can be written as a to the power n cube into a to the power r. Okay, and again applying the properties of a integral power of an element of a group, we have a to the power n whole to the power q into a to the power r is equal to e. So this implies this. So this equation is implies a to the power n whole to the power q into a to the power r, and it is equals to e. And you know that a to the power n, that means the order of an element A in a group G, and it is equals to n. That means a to the power n is equal to e. So from this we will get e to the power q, that means a to the power n is equal to e. So e to the power q into a to the power r. So this implies e to the power q into a to the power r, and is equals to e. And you know that the power of an identity element is identity. So from this we will get a to the power r is equal to e. So now n is the least positive integer such that a to the power n is equal to e. And since r is less than n, so the above result is possible only when r is equal to 0. Otherwise it is not possible. And from the definition of a order of a group, we know that a to the power n is equal to e, where n is the least positive integer. But in that case, a to the power r is equal to e, and r is the number is less than n. So it is not possible. And it is possible only when r is equal to 0. So therefore the remainder is 0. That means n is equal to n into q. And this implies n is a divisor of m. So this is the sufficient condition of the theorem 3. Or that means if a to the power m is equal to e, then n is a divisor of m, as well as if n is a divisor of m, then a to the power m is equal to e. This is the sufficient and the necessary condition of the theorem 3. So after that we will talk about the fourth theorem on the order of a group. So here is the theorem: if order of a is equal to n, then a square, a cube, and up to a to the power n, and a to the power n is equal to e. Okay, a to the power n is the identity element. So are the distinct element of G. And proof is not in your syllabus, so I neglect this proof of theorem 4. So after that we will take the fifth theorem on the order of a group. So let A be an element of a group G composition of order n, and P is a prime to n. Okay, so then the order of a to the power p is also n. That means order of a to the power p is equal to n. where P is the prime to N. Okay, so this is the theorem. So here is the proof of the fifth theorem on order of a group. So let order of a to the power P and it is equals to M. So we consider this. So then order of A is equal to N and it is given, and here A be an element in G. So the order of an element A is N. That means A to the power N is equal to E. And this imply a to the power n or to the power p and it is equals to e to the power p. After taking p as a power on both sides, we will get e to the power n whole to the power p is equal to e to the power p. Okay, so and you know that the power of an identity element is identity. So this implies a to the power p whole to the power n, that is equals to e. And in that case, we have applied the properties of a integral power of an element of a group. Okay, a to the power n to the power p, it is equal to a to the power p to the power n, and it is equals to e. So therefore, the order of a to the power p, it is less or equal to e. Okay. So and you know that order of a to the power p, I have considered order of a to the power p is equal to n. So from this we will get n is less or equal to n, and we can write it equation number 1. Again, since p and n are the prime to each other, so there exists an integer x and y such that px plus ny is equal to 1. From the number theory we have seen that, and therefore a to the power 1 and it can be written as a to the power px plus ny, where p and n are the prime to each other and xy are the integer. Then 1 is equal to a px plus nq. Then px plus ny is equal to 1. So therefore a to the power 1 is equal to a to the power px plus ny. So where you know that 1 is equal to px plus ny. Okay, so therefore this can be written as a to the power px into a to the power ny. And this equation is implies a is equal to a to the power px into a to the power n whole to the power y. So a to the power ny can be written as this, a to the power n whole to the power y. And you know that a to the power n is equal to e. This is the order of an element a, and it is equals to n. So a to the power n is equal to e. Okay, so from this we will get a to the power px into e to the power y. So in that case, a to the power n is equal to e, and e is the identity element. And you know that any power of an identity element is identity. So a to the power px into e to the power y, and it is equals to a to the power px into e, that is a to the power px. So therefore a is equal to a to the power px. Now taking m as power of both sides of an element, we will get a to the power m is equal to a to the power px whole to the power m. Okay, so this implies a to the power m is equal to a to the power p whole to the power m whole to the power x. And you know that order of a to the power p is equal to m. That means a to the power p whole to the power m is equal to e. So a to the power p whole to the power n, it is equals to e. That means a to the power m is equal to e to the power x, and you know that e to the power x is equal to e. Okay, where e is the identity element. And from the above equation we conclude that order of a is less or equal to m. And you know that order of a is equal to n. So therefore from this we will get n is less or equal to m. Okay, so order of a is equal to n, we know that. So n is less or equal to n. And we can write in equation number 2. Combining this equation 1 and 2, and from this we will get n is equal to m. This is the proof of the fifth theorem on order of a group. After theorem 5, we will take some examples on order of a group. So here is the example. If x comma y belongs to G composition, then so that order of y and order of x composition y composition x inverse are same. and hence or otherwise prove that order of A composition B is equal to B composition A. This is the second part of the example 1. Okay. So here is the solution of the given problem. So we'll start with the first part of the given problem. If xy belongs to G composition, so here G composition be a group, and then from this we will prove that order of y and order of x composition y composition x inverse are same. So let us consider order of y is equal to n. So from the definition of order of a group, we have y to the power n is equal to e. So e is the identity element, and from the definition of order of a group, we know that y to the power n is equal to e. So this is the identity element. Okay, so from this we will prove that the order of x composition y composition x inverse, and it will be n. Okay, so now x composition y composition x inverse whole square, and it is equals to x composition y composition x inverse composition x composition y composition x inverse. So you know that a square is equal to a composition a. So applying this, we will get x composition y composition x inverse whole square is equal to this. Now applying the associative property of group theory, we are seeing that x composition y composition x inverse composition x composition y composition x inverse. Okay, and you know that x inverse composition x, and it is equals to identity, and this is the inverse property of the group theory, where is the identity element in G. Then from this equation we get x composition y composition e composition y composition x inverse, and it is equals to, okay, and where is the identity element. So from this equation we get x composition y composition y composition x inverse, and you know that y composition y is equal to y square, and from this we get x composition y square composition x inverse. Okay, that means x composition y composition x inverse whole square, and is equals to x composition y square composition x inverse. Okay, after applying the properties of a group theory. Similarly, we will find x composition y composition x inverse whole to the power 3, and it is equals to x composition y to the power 3 composition x inverse. Applying the same properties of a group theory, we will find this x composition y composition x inverse whole to the power 3 is equal to this. Okay. So in general, x composition y composition x inverse whole to the power n, where n be any positive integer. So from this we'll get x composition y to the power n composition x inverse. Okay, you know that y to the power n, this is the order of y, and we have already considered this in the beginning of the solution. Y to the power n is equal to e. So y is the identity element, and from this equation we'll get x composition e composition x inverse. Okay, so x composition y composition x inverse whole to the power n, and it is equals to x composition x inverse. Y is the identity element, and you know that x composition x inverse, it is equals to e. This is the inverse properties of a group theory. Okay, so y is the identity element. So that means the order of x composition x inverse, and it is equals to n. That means order of y and order of x composition y composition x inverse are same. If possible, let x composition y composition x inverse whole to the power m is equal to e. So here we take m be any positive integer, okay, and the order of this is equals to e, and where m is less than n. So then x composition y composition x inverse whole to the power m, and it is equals to e. So from this we'll get x composition y to the power m composition x inverse is equal to e. So in that case I have applied the previous properties. That means x composition y composition x inverse whole to the power n is equal to this. Okay, so therefore x composition y composition x inverse whole to the power m, and it is equals to x composition y to the power m composition x to the power minus 1, it is equals to e. Operating x inverse on left and x on right of this equation, we get x inverse composition x composition y to the power m composition x inverse composition x, and it is equals to x inverse composition e composition x. And from the above equation we get e composition. So x inverse x is equal to e, you know that as is the identity element, and the composition y to the power m composition e, and it is equals to x inverse composition x. That means y to the power m is equal to e. So which is impossible, as the order of y and y is equal to n. But in that case the order of y is m and m is less than n. It is not possible, and I have already considered that the order of a group is n. So n is the least positive integer such that it is for n is equal to e. But when we take x composition y composition x inverse to the power m, that means the order of a element this, that means x composition y composition x inverse is m. So from this we will get y to the power m is equal to e, and this is impossible. Okay, so while m is less than n, so therefore n is the least positive integer, you know that. So such that x composition y composition x inverse is equal to n, that is order of x composition y composition x inverse is equal to n. So hence the proof of the first part of the example 1. Okay, so after that we'll take the second part of the above examples. A composition B composition A composition A inverse. So in that case y is equal to say B composition A. Okay, so A composition B composition A inverse. So and it is equals to, after applying the associative properties, from this we'll get A composition B composition A composition A inverse. Okay, so you know that A composition B composition A inverse A composition A inverse, and it is equals to E. So applying the inverse properties of a group, we will see that A composition A inverse is equal to E. So therefore from this we will get A composition B. So therefore order of A composition B composition A inverse, and it is equals to order of A composition B. Okay, so now taking order on both, we will get this one. And this imply, you know that order of A composition B composition A inverse, it is equals to order of A B composition A. In that case we apply the previous properties of the order of a group. What is the previous property? Order of y and order of x composition y composition x inverse are same. That means, so in that case order of A composition B composition A inverse, it is equals to the order of B composition A. So order of B composition A, it is equals to order of A composition B. So hence the proof of the second part of the given problem. Okay, and it is equals to order of B composition A is equal to order of A composition for all AB belongs to G. So after that we will take the second example on the order of a group. If y be an element of a group G composition and order of y is equal to 20, find the order of y to the power 8. So since order of y and it is equals to 20, so from the definition of a order of a group, y to the power 20 is equal to E, where E is the identity element in G. So now let order of y to the power 8 is equal to n. Okay, so that means from definition of order of a group, y to the power 8 whole to the power n, and it is equals to E, where E is the identity element. That is y to the power 8n is equal to E, where n is the least positive integer. Now applying the third theorem on order of a group, we are seeing that 20 is a divisor of 8n. Okay, so in that case where 20 is the order of a y, and while y is an element of G, and n is the order of y to the power 8, where n is the least positive integer. Then from theorem 3 we are seeing that 20 is a divisor of 8n. That means 5 is a divisor of 2n. So therefore n is equal to 5 as n is the least positive integer. So here 5 is the least positive integer. Okay, such that 5 is a divisor of 2n. So therefore order of y to the power 8 and it is equals to 5. Now move on the next slide. So in this slide we'll take a third example on the order of a group. See if in a group G composition a to the power 5 is equal to e and a inverse is equal to b square. Okay, so these two relations are given for all a b belongs to G. Find the order of b. Here is the solution. So now a inverse whole square, okay, and it is equals to, you know that from the group theory, a inverse into a inverse. Okay, so now applying the associative properties of a group theory, from the right of the above equation we see that AB into A inverse composition A, that means A inverse A into B A inverse, and it is equals to, you know that A inverse A, it is the inverse properties of a group theory, and it is equals to E. So from this we will get AB into E into B A inverse, and it is equals to A B into B into A inverse. Okay, so ID is the identity element. So from this we will get a b square is equal to a inverse, and you know that b square is equal to a b inverse. So this is also given. So from this we will get a into a b inverse into a inverse, and it is equals to a square b a inverse. Okay. So similarly we will find the value of that means a to the power minus 1 whole to the power 4, and it is equals to a inverse whole square into a inverse whole square. Okay, and we have already found that value, that means a inverse whole square, and it is equals to a square b inverse into a square b inverse. Okay, and applying the same thing from this 2, we will get a square into b into a to the power minus 2 into a square into b a to the power minus 2, and you know that a to the power minus 2 into a square is equal to a to the power 0, that means the identity. So a square b into a to the power 2, and it is equals to a square into b square into a to the power minus 2. Again putting the value of b to the power 2, that means a inverse, and from this we will get a square into a inverse of a to the power minus 2. That means a cube into b into a to the power minus 3. So therefore a inverse whole to the power 2, and it is equals to a square b a to the power minus 2. And after that we have find a inverse whole to the power 4, and it is equals to a to the power 3 b a to the power minus 3. So this way we will find a inverse whole to the power 8, and it is equals to a to the power 4 b a to the power minus 4. Applying the same thing we will get this one. Okay, and a inverse whole to the power 16, it is equals to a inverse whole to the power 8 into a inverse whole to the power 8. And for a inverse whole to the power 8 is equal to, you know that a to the power 4 b a to the power minus 4, and similarly this one is equal to a to the power 4 b a to the power minus 4. So, and applying the above process we will get from this a to the power 4 b square into a to the power minus 4, that means a to the power 4 into a inverse, where b square is equal to a inverse, okay, into a to the power minus 4. And after multiplying this or simplifying, and after simplifying this, we will get a to the power 5 b a to the power minus 5. And you know that a to the power 5 is equal to e. This is the order of a element a, and it is given. Okay, so e inverse, where a to the power minus 5 is equal to e inverse. Okay, where e inverse is equal to e as well. And the inverse of identity element is identity. So from this we'll get b into e, that is b. So thus b square whole to the power 16, you know that a inverse, and it is equals to b square. So b square whole to the power 16, and it is equals to b. Okay, or b to the power 32 is equal to b. So b to the power 32 can be written as b to the power 31 into b, and taking inverse on right on both sides we will get b to the power 31 into e. So where b inverse is equal to, you know, that is equal to e. So b to the power 31 is equal to e. So that means order of b is either 1 or 31, where 31 is a prime integer. Okay. So if b is equal to e, then order of b is equal to 1. So where e is the identity element, then order of b is equal to 1. And if b is not equals to e, then order of b is equal to 31. So okay, so in that case the order of b is either identity or prime number. So in that case order of b is equal to 31. So now we are move on the next problem on the order of a group. So if G composition be a group such that A composition B whole to the power n is equal to A to the power n composition B to the power n for the three consecutive integers in and for all A B belongs to G, then so that G is abelian. So here is the proof of the given problem. According to the problem, we have A composition B whole to the power n is equal to A to the power n composition B to the power n. So this relation is satisfied for three consecutive integers. Okay, so A composition B whole to the power n is equal to A to the power n composition B to the power n. We can write in equation number 1. A composition B whole to the power n plus 1, it is equals to A to the power n plus 1 composition B to the power n plus 1, and you can write in equation number 2. And A composition B whole to the power n plus 2 is equal to A to the power n plus 2 composition B to the power n plus 2, and we can write in equation number 3. So n plus 1 and n plus 2 are three consecutive integers. Okay. So now A composition B whole to the power n plus 2, and it is equals to, and from equation 1, 2 and 3 we will prove that G is abelian. So first of all we will take A composition B whole to the power n plus 2, and it is equals to in there A plus B whole to the power n plus 1 composition A plus B. Okay. And now applying the above properties, that means this property is given. So A to the power n plus 2 composition B to the power n plus 2. Applying the third relation, we will get A to the power n plus 2 composition B to the power n plus 2, and it is equals to A to the power n plus 1 composition B to the power n plus 1 composition A composition B. So the above equation is implies A composition, and A to the power n plus 2 it is equals to A composition A to the power n plus 1, as well as B to the power n plus 2 it is equals to B to the power n plus 1 composition B, and then applying the associative property we will get this one. Okay, so A composition A to the power n plus 1 composition B to the power n plus 1 composition B, and it is equals to again applying the associative property on the right of the above equation we will get this A composition A to the power n composition B to the power n. So in that case where A to the power n plus 1 is equal to A composition A to the power n plus 1, as well as B to the power n plus 1 is equal to B to the power n composition B plus A composition B, and applying the associative property we will get A to the power n plus 1 composition B to the power n plus 1, and it is equals to A to the power n composition B to the power n composition B composition A by the left and right cancellation law. So in that case, when A and B both terms are eliminated by applying the left and right cancellation law. So again applying the first and second relation on the given problem, that means A composition B whole to the power n plus 1, that means A to the power n plus 1 composition B to the power n plus 1, and A to the power n composition B to the power n, and it is equals to A composition B whole to the power n. So applying 1 and 2, that means the first and second relation will get this one. Okay, so composition B composition A, and again A composition B whole to the power n plus 1, it can be written as A composition B whole to the power n composition A composition B, and it is equals to A composition B whole to the power n composition B composition A. Again applying the left cancellation law, then from the above equation we have A composition B is equal to B composition A. That means A composition B is equal to B composition A for all A B belongs to G. So hence G, B and abelian. Understood? So after that we will take one more example on the order of a group. So here is the example. Prove that a group G composition is abelian if and only A composition B inverse is equal to A inverse composition B inverse for all A belongs to G. Okay, so here is the proof. Let A composition B inverse and it is equals to A inverse composition B inverse. This is given. Okay, and for all A B belongs to G, and from this we will prove that G composition be a abelian group. So then A composition B inverse whole inverse. So now taking inverse on both, we will get A composition B inverse of inverse. It is equals to A inverse composition B inverse of inverse. So A composition B inverse of inverse, it is equals to, you know, that A composition B. This is the properties of the group theory. Okay. So this is equals to B inverse of inverse composition A inverse of inverse. Okay. And you know that A composition B inverse is equal to B inverse composition A inverse. And this is the theorem on the group theory. Okay, so from this you know that B inverse of inverse is equal to B and A inverse of inverse is equal to A. So that means A composition B is equal to B composition A for all A belongs to G. That means G composition be an abelian group. Next, let G composition be an abelian group, and then from this we will show that A composition B inverse is equal to A inverse composition B inverse. So G composition be an abelian group, then A composition B is equal to B composition for all A belongs to G. This is the definition of the abelian group. Okay. So now taking inverse on both, we will get A composition B inverse is equal to B composition A inverse. Okay. So A composition B inverse is equal to A inverse composition B inverse. So you know that B composition A inverse is equal to A inverse composition B inverse. So therefore A composition B inverse is equal to A inverse composition B inverse for all A belongs to G. And this is the proof of the fifth example on order of a group. And after that we will take the sixth example on the order of a group. So that the group G composition be abelian if and only A composition B square is equal to A square composition B square. Let us move on the next slide. So in this slide we will take one more example on the order of a group. So that a group G composition is abelian if and only A composition B squared is equal to A square composition B square for all A belongs to G. So let G composition be an abelian group. Okay, so that means A composition B is equal to B composition A for all A belongs to G. Then A composition B whole square, and it is equals to A composition B composition A composition B. And now applying the associative properties on the group theory, we will see that A composition B composition A composition B, and it is equals to, you know, that A composition. So G is a abelian group, so A composition B is equal to B composition A. Okay, so we will take B composition A is equal to A composition B. And from this we will get A composition A composition B composition B. So we can, in that section we can apply the associative properties, and from this we will get A square composition B square. So that means A composition B whole square, and it is equals to A square composition B square when G composition be an abelian group. This is the necessary part. And next, conversely, let A composition B whole square is equal to A square composition B square, to show that G composition be an abelian group for all A belongs to G. So then A composition B square, it is equals to A square composition B square. Okay, so A composition B square, and it can be written as A composition B composition A composition B. And A square can be written as A composition A, and B square can be written as B composition B. Now applying the associative properties on both sides, we will get A composition B composition B, and it is equals to A composition B composition A composition B. Okay. Now applying the left and right cancellation law, and from the above equation we will get A composition B, and it is equals to B composition A for all A belongs to G. So hence G composition be an abelian group. After that, we will discuss about the congruent module M. So two integer a and b are said to be congruent module M if a minus b is divisible by the fixed positive integer a. And then we write a equivalent to b module M. Okay, so congruent relation can be written as this: a equivalent to b module M. That means a minus b is divisible by M, and which is read as a is congruent to b module M. For example, 18 equivalent to 3 module 5. So 18 minus 3 is divisible by 5. Okay, as well as 7 equivalent to 7 module 7. That is 7 minus 7 is equal to 0, and 0 is always divisible by any numbers. Okay. Again, minus 22 equivalent to 2. That means minus 22 minus 2, that means minus 24, and minus 24 is divisible by 6. And after that, we will define the residue classes module M. So as the congruence module M is an equivalence relation in Z. Okay. So as it forms a partition Z into M distinct equivalent classes, which are called residue classes module M or congruence classes module M. So they are denoted by within third bracket or bar. So that means 0 within third bracket, 1, 2 and up to n minus 1, or 0, 1, 2, 3 and up to n minus 1 bar. So it can be written either within third bracket or bar. So where A within third bracket, that means the residue classes of the element A, that is equals to x such that x belongs to Z, and x minus a is divisible by m. Okay, is the definition of the residue classes module M, and which denote the set of all residue classes module M in Z by Zm, and thus Zm is equal to, so Zm there are m elements, so the first element is 0, 1, 2, 3 and up to m minus 1, and within third bracket, or 0 bar, 1 bar, 2 bar and up to m minus 1 bar. And residue class 0 is called the 0 residue class. Okay, and is denoted by 0 within third bracket or 0 bar. So here is the example of congruent module M. So for example Z4. So in that case, where M is equal to 4, and Z4 is equal to, you know, that 0, 1, 2, 3. So there are 4 elements: 0, 1, 2 and 3. Where 0 is equal to 0 plus minus 4 plus minus 8 and up to infinity. Okay. 1 is equal to 1, 1 plus minus 4, 1 plus minus 8 and up to infinity. 2 is equal to 2, 2 plus minus 4, 2 plus minus 8 and up to infinity. And 3 is equal to 3, 3 plus minus 4, 3 plus minus 8 and up to infinity. And 4 is equal to, it is again 0. That means 0 plus minus 4 plus minus 8. Okay. And this is called the congruent module 4. So here is the example on congruent relation, so that the set of non-zero residue classes module 4 does not form a group with respect to multiplication of residue classes. So let Z4 be the set of all non-negative residue classes. So in that case, where Z4 is equal to 1, 2 and 3, 0 is not included. So Z4 is the non-zero residue classes. So 0 is the 0 residue classes. So now, omitting the bracket, we construct the following composition table. So 1, 2, 3, and similarly, this is actually the composition table. Okay, the row, the top row it is 1, 2, 3, and the first column it will be 1, 2, 3, and the operation is multiplication. So 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3. You know that. 2 into 1 is 2, 2 into 2 is 4, and in Z4 it is equal to 0. 2 into 3 it is equal to 6. So in module 4 we will get 2. Okay, module 4. So it is equal to 2. 3 into 1 is 3. 3 into 2 it is 6. So that means 2. And 3 into 3 it is 9. So after divided by 4 we will get 1. That means 9 minus 1 is equal to 8. So that is 9 is equivalent to 1 module 4. Okay. So therefore, From the above, we see that 2 into 2, that means 0, and 0 is does not belongs to Z4. So Z4 is not closed with respect to the multiplication of residue classes. Okay, so the closure property is not satisfied in that case. So hence Z4 cross does not form a group. So I will stop here today's lecture. Thank you.